All right, so Kafka. Imagine, right, you're building this app, and it needs to track stock prices live as they change. You'd have tons of updates coming in every second. You can't lose any of them. And oh yeah, more and more people keep using your app.
Sounds like a challenge.
It is. And that's where Apache Kafka comes in. Today, we're going to really dive deep into Kafka. And not just like what it does, but how it actually works.
We're going to make sure, even if you're new to Kafka, you can follow along. It's like Kafka's this really well-organized system for your data. We'll break down how it makes sure your data gets where it needs to go safely and reliably. No need to get lost in the technical weeds.
I like that, a well-organized system. So let's start with something called partitioning.
Right, so partitioning. Imagine your stock app. Suddenly, it's getting millions of updates per second all at once. Trying to process all that on one computer, disaster waiting to happen.
Makes sense. Too much for one computer to handle.
So partitioning splits that huge amount of data into smaller, more manageable chunks. We call those partitions. Think of it like having multiple lines at the post office. Way better than everyone crammed into one giant line, right?
Definitely. So we're dividing the work, but how does Kafka know which line or partition to put each piece of data into?
Good question. That's where keys come in. Imagine each of those stock updates has a key. Maybe it's the stock symbol, like AAPL for Apple or GUOB for Google. Kafka can use that key to make sure all the updates for the same stock always go to the same partition.
So everything stays organized.
Exactly. That way we can process all the Apple updates in the order they happened. It keeps things running smoothly.
Got it. So it's not just dividing the work, it's keeping it neat and tidy too. What if, let's say, there's no obvious key for the data?
Kafka's got that covered. It's smart. It'll use something called a round-robin approach. Basically, it just distributes the data evenly across those partitions. Kind of like dealing cards, one to each player, making sure no one gets overloaded.
So even without keys, it's still balancing things out.
Yeah, exactly.
Now, on the other end, we need something to actually read all this data, right? So that's where consumer groups come into play.
Yep. Consumer groups are like our team of workers all ready to process those stock updates. So let's say you have 3 workers in a group. Kafka, very cleverly, it will assign each worker to a specific partition. That way, none of them are duplicating each other's work.
Ah, so it's all about teamwork.
Right. And the best part is, if we need to add another worker to the group, to handle even more data, Kafka can do that too.
Okay, so how does it add a new worker without messing everything up?
It does this cool thing called rebalancing. When that new consumer joins the group, Kafka redistributes those partitions, making sure everyone gets a fair share of the work.
Rebalancing, I like that. It sounds like a delicate dance.
It is, sort of.
But are there any, downsides to this whole reshuffling?
Well, there can be a tiny hit-up, a very small delay, while Kafka is doing that rebalancing, just to make absolutely sure no data gets lost or, accidentally processed twice.
So like a brief pause, just to get everything in order. Okay, that makes sense. But what happens if, let's say, one of those servers running Kafka, a broker, we call them, what if one crashes? Does that mean everything comes to a screeching halt?
That's the great thing about Kafka. It's designed for exactly this. It uses something called replication. Basically, it's like having backup copies of each partition. If one broker goes down, another one can take over.
Backup servers, always a good idea. But how does Kafka make sure those backups are, up to date?
So each of those partitions, it has a leader. This leader, it handles all the reading and writing for that partition. Then you've got follower replicas. They're like mirror images. They're copying all the data from the leader. Now, if that leader crashes, a follower is ready to step up and become the new leader. Keeps everything running smoothly.
That's really clever. So even with a crash, the data keeps flowing. But how about making absolutely sure each of those stock updates, those little pieces of data, how do we make sure they actually get delivered?
That's where delivery guarantees come into the picture. And Kafka gives you some choices here.
Choices are always good. So what are our options?
First up, you've got at most once. This one's all about speed. Think of it like sending a postcard. You just send it, no tracking, no guarantee it arrives, but it's fast.
Risky but fast. What's next?
All right, so next we have at least once. Now we're talking, it's like sending a package, but with tracking. So it might take a bit longer, but Kafka will keep trying to deliver that message until the consumer, the one receiving it, says, got it. The only thing is, there's a tiny chance you might get a duplicate message if things get a bit messy.
Okay, so it's more reliable, but there's that trade-off with potential duplicates. And what's the, top-tier option?
The gold standard is exactly once. Imagine it like a certified letter someone has to sign for it. This one were more complex to set up, but it guarantees you each message is delivered only once. No duplicates, even if there are retries happening behind the scenes.
So you pick your guarantee based on how important it is that every single message gets through. Speed versus reliability, classic trade-off. But how does Kafka actually keep track of all these messages? It seems like, a massive amount of information to manage.
Right, that's where offsets come in. They're like bookmarks. They mark the last message that was processed in each partition. That way, if a consumer needs to restart, they know exactly where to pick up from.
Like those little sticky notes we used to mark our page in a book. Got it. But who manages these bookmarks?
You have options there too. Kafka can manage them for you, keeps things simple, but you don't know as much control. Or you can do it manually, gives you more control, but you got to be careful not to create duplicate bookmarks that can lead to problems.
So automatic is easier, manual gives you more control, but with more responsibility. Choices, choices. Now, who is like the librarian in this whole Kafka setup? Who keeps everything running smoothly?
That would be the Kafka controller. It's a special broker and it acts like the brains of the operation, keeps track of which broker is the leader for each partition, and it handles other important cluster-wide tasks.
The one in charge. But how does it talk to all the other brokers? How does it keep everyone in sync?
It uses a service called Zookeeper. Think of Zookeeper like a shared notebook where all the brokers can write and read crucial information about the cluster. Keeps everyone on the same page.
Like a central bulletin board for Kafka. Got it. Now, what happens if that controller, if it crashes? Does the whole system come crashing down?
Nope, not at all. Kafka's got that covered. If the controller goes down, another broker gets elected to be the new controller. The library stays open for business.
Phew, crisis averted. But, in the real world, things change. What if we have to add a new piece of information to those stock price updates? Does that break everything?
That's a great point and leads us to schema evolution. See, data changes all the time. Kafka uses something called a schema registry to manage those changes to make sure nothing breaks.
Schema registry sounds interesting. Tell me more about it.
It's like, imagine you have this blueprint for how your data should look. When you change the data, you register that new blueprint, that new schema with the registry. It checks if your new version is compatible with the old one, helps prevent breaking changes.
So it's like a compatibility checker. Make sure all the systems can still talk to each other. What if we absolutely have to make a change that isn't compatible? Can we do that?
It depends, how big the change is and how your system is designed. Kafka has different levels of schema compatibility. There's backward, forward, and full.
Okay, break those down for me.
All right, backward compatibility means that the older systems, they can still understand the new data, even if it has some extra information they don't need. Forward compatibility means the opposite. New systems can read old data, even if it's missing some stuff. Full compatibility means both ways work.
So it's all about planning and careful changes so we don't break things. Let's get specific. What happens if we add, like, a new field to those stock price updates?
If that new field has a default value, it's usually backward compatible. The old systems, they can just ignore it.
So like adding a new optional section to a book. Old readers can skip it. What if we don't set a default value?
Then it gets trickier. Old systems, they might not know what to do with that new field. They could even crash. So in that case, you'd need to update those older systems before you start sending out the new data format.
Makes sense. Don't want to crash any systems. What about removing a field? Is that ever a good idea?
Removing fields can be tricky too. If it's a field that maybe wasn't that important, maybe not everyone was using it, then you can probably remove it without too much trouble. But if it's crucial, you need to make sure everyone who's using that data is updated before you go removing it.
All right, so schema evolution is all about careful change management. Got it. Now, what about Kafka's memory, with all this data streaming in? How do we prevent it from basically exploding?
That's a great question because data can really pile up. But Kafka has some smart ways to manage all that storage and make sure the data stays relevant. First up, we have retention policies. They're like expiration dates for our data.
So we're setting a limit for how long we keep data around.
Yep, you can configure Kafka to delete data after a certain amount of time, like, say, 7 days. Or you could set a limit based on the size of the data. Once it hits that limit, boom, older data gets deleted.
Keeps things tidy. But what if we need to keep some data forever, like at the very latest stock price?
For that, we have message compassion. It's like, instead of keeping every edition of a book, we only keep the most recent one. Older versions get discarded, keeps things efficient and focused on the current information.
So we're only keeping the latest and greatest data. What kind of data would benefit from this compaction?
It's perfect for things like, like those stock prices you mentioned, or user profiles. We're not interested in all the historical data, just the current state of things.
Got it. Compassion helps keep storage under control. Now let's talk about something that's really exciting. Real-time processing with Kafka Streams. This is where things get really interesting.
Kafka Streams is powerful stuff. It lets you build applications that analyze and react to data as it's flowing through Kafka in real time. Imagine like a sorting machine right on the conveyor belt. It can categorize and act on packages as they're moving along.
Powerful is right. But before we get carried away, can you give us a breakdown of how Kafka Streams works? Some of the core ideas?
Sure. So first we have the concept of a stream. pretty simple. It's just that continuous flow of data, like our conveyor belt.
Okay, that makes sense.
Then we have K-stream and K-table. So a K-stream represents the raw data flowing through, like those packages on the conveyor belt. A K-table, on the other hand, it's more like a continuously updated summary of the data. Like, imagine a digital inventory that changes as packages get processed.
So K-stream is the flow, and K-table keeps track of the current state.
You got it. And these are like the building blocks for making smart applications that can react to data as it comes in.
So what makes Kafka Streams so special? Why not use other tools?
Well, for one, it's built right into Kafka, so you don't have to manage separate systems, which is always nice. Also, it's designed for real-time work, meaning you can react to data the instant it arrives. And just like Kafka, it scales really well and handles failures gracefully.
I can see why people get excited about this. Can you give us some real-world examples of what you can do with Kafka Streams?
Absolutely. Let's say you want to track social media trends. Kafka Streams can analyze hashtags in real time, calculate how often they appear, and even detect unusual activity like a sudden surge in mentions.
So you're not just moving the data, you're getting insights from it as it's happening. That's pretty impressive. Any other cool examples?
Oh, tons. You could use it to enrich data. Imagine you have a string of purchase orders. Kafka Streams can combine that with, say, customer data from another source. This allows you to personalize recommendations or offers in real time.
Wow, that's powerful. Kafka Streams definitely opens up a whole world of possibilities. But with all this data flying around, we can't forget about security, right?
Absolutely. Security is paramount, especially when you're dealing with sensitive data. And Kafka has some really strong security features to keep your data protected.
Right, we mentioned SSL/TLS encryption earlier. It's like having those secure tunnels for our data as it travels between systems.
Exactly. To use encryption, you need to configure both Kafka and the clients that connect to it with certificates. They're like digital ID cards. They ensure that everyone is who they say they are and that no one can sleep on the data.
So it's about verifying identities and keeping the data private. What about, like, access control within Kafka itself? Can anyone who connects just read and write whatever they want?
Nope, not at all. Kafka uses access control lists. We call them ACLs. They're like really specific permission rules. You can control exactly which users or applications can read from, write to, or even manage different parts of Kafka.
So it's like different levels of access within a company, right? Some people can read confidential files, others can only access public information. What about compliance with, all those data privacy regulations? Does Kafka help with that?
Absolutely. All those security features we've been talking about, they're designed to help you comply with regulations like GDPR and CCPA. Encryption keeps sensitive data private, and ACLs help you enforce those access control rules, making sure only authorized people can see certain information.
So Kafka helps us stay secure and compliant. But what about keeping an eye on things? How do we monitor all this and make sure everything is running smoothly?
Monitoring is crucial. Kafka gives us a bunch of tools and techniques to keep track of the cluster and make sure it's healthy.
Okay, give us the rundown. What tools do we need?
One common combination is Prometheus, which collects all sorts of performance data, and Grafana, which helps us visualize that data in nice dashboards. Prometheus is like the sensor, and Grafana is the dashboard in your car giving you all the readings.
So we can see things like how much CPU is being used, memory consumption, all of that.
Exactly. And Kafka itself provides a ton of data through something called JMX, the Java Management Extensions Interface. This lets you really dig deep into what's happening inside Kafka.
Sounds comprehensive. But with all these metrics, what should we actually be focusing on? What are the signs of a healthy Kafka cluster?
There are a few key things to watch. First, you want to monitor those brokers, those servers running Kafka, make sure they're not overloaded and have enough resources. You should also check that partitions are balanced, spread out evenly across the brokers, so you don't have one broker doing all the work.
Makes sense. Anything else?
Consumer lag is an important one. This tells you how far behind consumers are in processing messages. If there's a lot of lag, it could mean they're having trouble keeping up.
So it's like checking if our package handlers are falling behind schedule. Got it. What else should we be watching for?
We also want to watch out for under-replicated partitions. If a partition isn't fully replicated, those backups we talked about, then it's vulnerable to data loss if a broker crashes.
Right, we need those backups to be ready to go. So keeping an eye on all these metrics helps us manage Kafka and make sure it's running smoothly.
Exactly. It's all about proactive management and making sure things are in good shape.
This has been incredibly helpful. We've gone from the basics all the way to some pretty advanced features. It's amazing how much complexity Kafka handles behind the scenes.
It's really quite a remarkable platform designed to tackle those tough data challenges head on.
I agree. Now, before we move on, let's circle back to Kafka Streams for a moment. We talked about the main ideas, but how about in practice? What does it actually look like to build an application using Kafka Streams?
Building a Kafka Streams application is like putting together a data processing pipeline. You have a few key steps. First, you got to define your data sources and sinks, like where's the data coming from and where's it going. This usually means figuring out which Kafka topics you're going to be reading data from and which ones you're going to be writing data to.
So we're mapping out the journey for our data. Got it. What's next?
Next, you got to define the processing logic, like what do you actually want to do with this data? This is where those K-stream and K-table concepts come in. You use them to transform the data, filter it, maybe aggregate it or enrich it. Think of it like setting up a series of operations along that conveyor belt, doing something to each package as it moves along.
Right, we're defining the actions we want to take. Can you give us a simple example just to illustrate how this works?
Sure, imagine you're getting a stream of data from sensors like Internet of Things devices. You could use Kafka streams to filter that stream. Maybe you only want to see readings that are above a certain threshold. Maybe that indicates a problem. Then you could use a K-table to keep track of each device's status and update it based on those sensor readings.
So it's not just watching the data go by, we're actively responding to it and updating our understanding in real time. That's really cool. So what happens once we've defined the processing logic? What's the next step?
Next, you create what we call a Kafka streams topology. It's basically a blueprint that connects those data sources, the processing logic, and the data sinks. It defines how data flows through your application, which streams and tables are connected, and how the data gets transformed as it moves through each stage.
It's like a flow chart for our data processing pipeline, visualizing the whole thing.
Exactly. Once you have that topology, you create a Kafka Streams instance and start it up. It connects to your Kafka cluster, and then boom, it starts processing data according to the plan you laid out in the topology, reads data from the source topics, applies your processing logic, and writes the results to those sync topics.
We hit the go button and the engine starts running. Are there best practices for building these Kafka Streams applications, things we should keep in mind to make them efficient and robust?
Definitely. One key principle is try to design your applications to be stateless whenever possible. That means avoid doing anything that requires storing information within the application itself.
Stateless. Okay. Why is that so important? What's the advantage?
Stateless applications are way easier to sustain, and they're much more resilient to failures. You see, if a Kafka Streams instance crashes, another instance can take over immediately without missing a beat. That's because all the important information is stored externally in those Kafka topics, not within the application itself.
So it's all about resilience, being able to handle failures gracefully. But what if we absolutely need to keep some state within our application? Is there a way to do that safely?
If you really need to maintain state, Kafka Streams provide something called state stores. They're basically persistent key value stores tightly integrated with Kafka Streams. Think of it like a dedicated memory space where you can store and update information as data flows through your application.
So it's like a built-in scratch pad for keeping track of things. Are there any other best practices, things we should keep in mind when designing Kafka Streams applications?
For sure. Keep your topologies simple, break them down into smaller modular units, makes them easier to understand, to test, and to maintain. And always, always leverage Kafka's built-in parallelism and fault tolerance features. This ensures that your applications can handle those massive data volumes and gracefully recover from any hiccups.
Solid advice. Simple, modular, and resilient. Got it. Now let's shift gears a bit and go back to security. We touched on it earlier, but I'd love to dive a little deeper, maybe talk about some specific security features and best practices for keeping those Kafka deployments secure.
Of course. Security is absolutely essential, especially when we're talking about sensitive data on the move. As we mentioned before, encryption is your best friend. Using SSL/TLS encryption for Kafka makes sure the data traveling between producers, consumers, and brokers is protected.
Right, like having those secure tunnels for our data. How do we actually set up this SSL/TLS encryption? What are the steps?
All right, so to get SSL/TLS working, you need to configure both your Kafka brokers and the clients connecting to it with the right certificates and key scores. These are like digital ID cards. They prove that each participant is legit. The brokers, they need a certificate that's signed by a trusted certificate authority. And the clients, they need a key store that holds their private key, which goes with their certificate.
So it's like a secure handshake between the systems, making sure everyone's who they claim to be. What about authentication? How does Kafka actually confirm the identity of users and applications trying to connect?
Kafka has a couple of ways to do this. There's SSL authentication and SSL authentication. With SSL authentication, clients, they show their digital certificate to the broker when they first connect. The broker checks it out, makes sure it's valid and trusted, and then grants access.
So it's like showing your ID to get into a club. What about SSL authentication? How does that work?
SSL authentication, it's more flexible. It can handle different ways of authenticating, like Kerberos, plain text passwords, and even custom plugins if you need something special. It's basically a framework for securely connecting clients and brokers using different authentication methods.
So it gives you options depending on your security needs. But even with authentication, how do we make sure that once someone's connected, they can only access the data they're supposed to?
That's where those access control lists or ACLs come in. They let you get really specific about permissions, who can do what within the Kafka cluster. You can say which users or applications can read from certain topics, write to them, create new topics, delete them, even manage those consumer groups.
So it's like having different levels of security clearance, right? Like in a government agency, some people have top secret clearance, others can only access public information. Can you give us an example of how you might use these ACLs in a real-world scenario?
Sure. Imagine you have a Kafka cluster that's used by different teams in your company. Maybe you want to let the marketing team read data about customer activity, but you don't want them to change it, so you'd give them read-only access to that topic. But then your data science team, they need full access to sensitive customer data for analysis, so you'd give them different permissions.
Makes sense. So ACLs are like fine-grained control over who can do what with the data. But what about keeping track of all this activity? For auditing purposes, or if we need to prove we're complying with regulations, does Kafka have a way to do that?
Absolutely. Kafka has built-in support for audit logging. You can configure it to keep a record of things like who tried to log in, any changes to the Kafka setup, even which messages were produced or consumed.
So it's like a security camera, capturing everything that happens in Kafka. What do we typically do with these audit logs? Where do they go?
You'd usually store these logs in a central place and then analyze them. You can look for potential security breaches, see if anyone's trying to do something they shouldn't. You can also track how data is being accessed, make sure everything's above board, and make sure you're following regulations like GDPR, which says you got to keep records of how you're processing data. Plus, these logs can be super helpful if you ever need to investigate a security incident, like a data breach.
Right, like a forensic investigation. So Kafka gives us encryption, authentication, authorization with those ACLs, and then auditing. It's like a full security package.
You got it. And remember, security isn't something you just set and forget. You got to constantly be reviewing and updating your security policies, your configurations, the whole 9 yards, because the bad guys are always coming up with new tricks.
Security is definitely a journey, not a destination. Now let's switch gears again and talk about monitoring Kafka's performance. We talked about monitoring tools earlier, but I'm curious, what are the specific things we should be tracking to make sure our Kafka cluster is healthy and running at peak performance?
Excellent question. To keep Kafka humming along, we need to keep a close eye on a few key areas. First up, we want to monitor the health of those brokers, those servers that are doing all the heavy lifting. We need to make sure they're not overloaded and have enough resources to handle the workload.
Okay, so what specific metrics should we be looking at to assess broker health? What are the telltale signs that everything is running smoothly?
Some important metrics to watch include CPU utilization, memory usage, network throughput, and disk I/O. You want to make sure these metrics are within a healthy range and there aren't any sudden spikes or dips that could indicate a problem.
So it's like keeping an eye on the gauges on your car's dashboard, making sure everything's within the normal operating range.
Exactly. Another crucial metric is partition distribution. You want to ensure those partitions, remember those chunks of data we talked about, are evenly spread across all the brokers in your cluster.
Right, so it's like making sure all the checkout lanes at the grocery store are being used so no one lane gets backed up. What happens if we have an imbalanced partition distribution? What are the potential consequences?
If one broker is handling way more partitions than the others, it can get bogged down, while others might be sitting there with nothing to do. This can create bottlenecks and slow down the whole system.
So it's all about balance, making sure the workload is distributed evenly. How do we actually monitor partition distribution? What tools or techniques can we use to get visibility into this?
There are some great tools out there like Kafka Manager or Control Center. They provide a visual representation of your Kafka cluster and show you how those partitions are spread out across the brokers. You can also look at metrics like the number of leader and follower replicas on each broker to get a sense of the workload balance.
Got it. So we have visual tools and specific metrics that can help us assess partition distribution. What other key metrics should we be monitoring? What else can give us insights into the overall health and performance of our Kafka cluster?
Consumer lag is another important one to keep an eye on. Remember, this measures how far behind consumers are in processing messages from their assigned partitions.
Right, like checking if those packet handlers are keeping pace with the incoming flow. We want to make sure they're not falling behind. What are some common reasons for high consumer lag? What could be causing those package handlers to struggle?
There could be a few things going on. It could be that the consumer application itself is slow. Maybe it's having trouble processing messages quickly enough. Or it could be that the consumers simply don't have enough resources, not enough CPU power, memory, or network bandwidth to handle the data flow. And sometimes it's just that there's a backlog of messages in the Kafka topic itself, meaning there's more data than the consumers can handle at the moment.
So if we see high consumer lag, we need to do some detective work and figure out what's causing it. What tools can we use to keep tabs on consumer lag? How do we get those insights?
Luckily, Kafka provides metrics specifically for tracking consumer lag. You can see the lag for each consumer group and each partition. Tools like Prometheus and Grafana, which we talked about earlier, can visualize these metrics beautifully and even send out alerts if the lag goes above a certain threshold.
Ah, so we can get proactive notifications if things start to fall behind. That's super helpful. Any other performance metrics we should be paying close attention to? What else is on the must-watch list?
Definitely. Another important metric is the number of under-replicated partitions. Remember, Kafka relies on replication to make sure we don't lose data if a broker fails.
Right, those backups are crucial for fault tolerance.
Exactly. If a partition is under-replicated, it means we don't have enough copies, which makes us vulnerable to data loss if a broker crashes.
So it's like making sure we have enough spare tires just in case we get a flat. How do we monitor for under-replicated partitions? What tools or techniques can we use to keep track of this?
Kafka gives us metrics that show the replication status of each partition. We can see if it's fully replicated or if any replicas are missing. And of course, we can use our monitoring tools to visualize these metrics and trigger alerts if the number of under-replicated partitions goes above a certain limit. That way, we'll be notified immediately if there is a potential risk of data loss.
So we're covered on all fronts: monitoring broker health, checking partition distribution, keeping tabs on consumer lag, and watching out for under-replicated partitions. That gives us a pretty comprehensive view of our Kafka cluster's performance and health. But monitoring is more than just collecting metrics. Are there any general best practices, things we should keep in mind to make sure our monitoring is effective?
That's a great point. Monitoring is most effective when it's driven by purpose. So before you even start collecting data, take a step back and define your monitoring goals. What are the key performance indicators, the KPIs, that matter most for your applications and your business objectives? What will you absolutely need to know to make sure everything's running smoothly and meeting its goals?
So we need to define what we're looking for, right? Align our monitoring efforts with what's important. What else should we consider?
You also want to choose the right monitoring tools for your specific needs. There are tons of tools out there, both open source and commercial, and they each have their strengths and weaknesses. Prometheus and Grafana are a popular combo, but you also have options like Datadog, New Relic, and Splunk, which are more full-featured monitoring platforms.
Right, it's about finding the tools that fit your environment and your budget. Any other tips for effective monitoring?
Yes, be smart about your alerts. You don't want to get flooded with notifications for every little blip in the metrics. Focus on setting up alerts for critical events, things that need immediate attention, like if a broker goes down, or consumer lag spikes way up, or the number of under-replicated partitions starts climbing. Those are the things that need your attention ASAP.
So prioritize the alerts. Focus on the ones that really signal a problem.
Exactly. And one last thing, make sure you have a plan for what you're going to do if you get an alert. Who's responsible for handling different types of issues? How do you escalate things if they get serious? Having a clear plan in place can make a world of difference in how quickly and effectively you can respond to problems.
Right, monitoring is only useful if you act on the information it gives you. It's about closing the loop, using those insights to keep things running smoothly. This has been a fantastic deep dive into Kafka's performance monitoring. It's clear that a lot of thought and care goes into making sure Kafka performs at its best.
Absolutely. It's a testament to the incredible work of the Kafka community and the importance of reliable data infrastructure in today's world.
Couldn't agree more. Now let's shift gears one last time and talk about something that's becoming more and more important: data governance. With all this data streaming and processing power, how does Kafka fit into the bigger picture of managing data responsibly and complying with regulations?
That's a great question. Data governance is all about managing data throughout its entire life cycle, from creation to deletion, making sure it's handled properly every step of the way. We're talking about data quality, security, privacy, and compliance with regulations like GDPR and CCTA.
So it's about treating data like a valuable asset, making sure we're doing the right thing with it. How does Kafka play into this?
Kafka actually has some great features that support data governance. Things like data lineage, which is being able to track where data came from and how it's been transformed, data quality monitoring, data access control, and data retention policies.
Okay, break those down for me. What is data lineage exactly, and how does Kafka help us with that?
Data lineage is all about tracing the origins of your data. Where did it come from? What systems has it passed through? What operations have been performed on it? It's like having a detailed history of the data's journey.
So it's like a family tree for our data. How does Kafka help us create this family tree?
Well, one of Kafka's strengths is that messages can't be changed once they're written. They're
Yeah.
immutable. And within a partition, messages are always delivered in order. That's a really strong foundation for tracking lineage. By storing metadata with each message, like the source topic, timestamp, processing steps, we can reconstruct the data's entire path.
So we have this audit trail. We can see exactly where the data came from and what happened to it. Super important for compliance, especially if we need to prove we're following the rules. What about data quality monitoring? How does Kafka help us make sure the data flowing through our systems is accurate and meets our standards?
Kafka Streams is a great tool for this. Remember all that real-time processing power? We can use it to implement data quality checks, define rules, set constraints, and validate data as it's coming in. If something looks wrong, we can trigger alerts or even take corrective actions automatically.
So it's like having an automated quality control system, making sure everything meets the standards. What about controlling who has access to the data? We talked about ACLs earlier, but are there any other features that help with data governance in this area?
ACLs are definitely a big part of it, but Kafka also has some other features that can enhance data governance, like topic-level replication and consumer group isolation.
Okay, tell me more about those. How do they help with data governance?
So, topic-level replication lets you decide which brokers or data centers can host copies of a particular topic. This can be really important for meeting data residency requirements, those rules that say where certain types of data can be stored. Or maybe you want to keep really sensitive data in a special environment with extra security.
So it's about controlling where the data lives, making it stays in the right place.
Exactly. And consumer group isolation, this prevents consumers from accidentally getting access to data they shouldn't be able to see. Each consumer group gets a unique ID, and Kafka makes sure they only get messages from topics that are specifically allowed for their group. Helps prevent accidental data leaks.
So we're adding extra layers of protection, making sure the right people and applications can access the data. What about data retention policies? How long do we keep the data around, especially when we have regulations that tell us how long certain types of data need to be stored?
Kafka's got you covered there too. With its retention policies, you can decide how long data stays in a topic before it's automatically deleted. You can set these policies based on time, like deleting data after a week, or based on size, maybe you delete data when the topic reaches a certain storage limit. It gives you flexibility to balance your data retention needs with storage costs and regulatory requirements.
Right, like having an automated cleanup crew that removes old data based on the rules we set. So Kafka helps us with data lineage, data quality, access control, and retention. It's like a data governance toolbox.
Exactly. These features can be really powerful allies in your data governance journey.
It's really interesting to see how Kafka, this platform known for its power and speed, also has these features that help us manage data responsibly. By using these tools, we can build systems that are not only high-performing, but also secure, compliant, and ethical.
Well said. It's all about finding that balance between performance and responsibility.
Absolutely. Now, before we wrap things up, let's take a quick peek into the future. What's on the horizon for Kafka? What exciting developments and trends should we be watching for?
Great question. The Kafka community is always innovating. One major development is the move away from Zookeeper towards something called KRaft for managing the cluster's state.
Right, we mentioned KRaft earlier in passing. Remind me again, what is it and why is this transition such a big deal?
KRaft is a consensus protocol that's built right into Kafka. Eventually, it will replace Zookeeper, which means Kafka will be able to manage itself without needing an external dependency. This makes Kafka similar to deploy and manage, more scalable and more robust. It's like Kafka's graduating to a more mature and independent platform.
So Kafka is becoming more self-sufficient. Cool. What other exciting advancements are on the horizon? What's next for Kafka?
Another big area of development is tiered storage. This involves moving older, less frequently accessed data to cheaper storage, like cloud object storage, while keeping the most recent and active data on faster, more expensive storage.
It's like having a smart library that automatically moves the less popular books to the back shelves while keeping the bestsellers up front, right? Makes sense. You want the most used data to be easily accessible.
Exactly. Tiered storage helps keep costs down without sacrificing performance.
What else should we be watching for in the Kafka world? What trends are shaping the future of stream processing?
Integration is a big one. We're seeing more and more efforts to seamlessly connect Kafka with other tools, especially in the areas of data processing and analytics. There's a lot of work happening to integrate Kafka with things like Apache Flink, which is a very powerful stream processing engine, and Apache Spark, a general-purpose distributed computing framework. These integrations combine Kafka's strengths in data ingestion and distribution with the analytical power of these other tools, allowing you to build some really sophisticated data pipelines and applications.
So Kafka is becoming more and more connected to the wider world of data. It's not just a standalone platform anymore. What about the cloud? How is Kafka evolving in the cloud-native world?
That's a huge trend right now, are seeing more and more Kafka deployments in the cloud, and cloud providers are offering managed Kafka services that make it super easy to get started. These managed services take care of a lot of the infrastructure complexities so you can focus on building your applications without having to worry about managing servers and clusters.
So it's like Kafka's getting a cloud makeover.
Exactly. And these managed services often come with extra features like automatic scaling, built-in fault tolerance, and seamless integration with other cloud services. It's making it easier than ever to leverage Kafka's power in the cloud.
So Kafka's becoming more accessible, more integrated, and more cloud-friendly. It seems like it's well positioned for the future of data, especially as we see more and more data being generated and used in real time.
Absolutely. Kafka's ability to handle massive data streams reliably, combined with its growing ecosystem and its embrace of the cloud, make it a platform to watch. It's going to be exciting to see what the future holds for Kafka.
Well, we've covered a lot of ground in this deep dive into Kafka. We started with the basics, explored advanced features, looked at security, performance, and even got a glimpse into the future. It's been quite a journey.
It has, and it's just the beginning. There's always more to learn and explore with Kafka.
Exactly. So, as we wrap up, what are some key takeaways you'd like to leave our listeners with? What are the most important things to remember from our deep dive? I think one of the biggest takeaways for me is just how versatile Kafka is. It's not just about moving data from point A to point B. It's a whole platform for building these really sophisticated data-driven applications.
It is. It's really evolved over the years.
If our listeners are just getting started with Kafka, what are like the most important concepts to grasp? Where should they focus their energy?
Well, I'd say start with those fundamentals we talked about: partitioning, replication, and delivery guarantins. Once you understand those, a lot of the other pieces start falling into place.
Right, those are like the foundational building blocks of Kafka. Master those, and you're well on your way.
Exactly. And don't be afraid to experiment. Spin up a Kafka cluster, play around with some of the features, try building a simple application using Kafka streams. There are tons of resources online, tutorials, blog posts, you name it. The Kafka community is incredibly helpful and welcoming.
The community is amazing. I've definitely found that to be true. They're always willing to help and share their knowledge.
For sure.
So as we wrap up this deep dive into Kafka, is there anything else you'd like to add? Any final thoughts or words of wisdom for our listeners?
I'd just say, as you're learning and experimenting with Kafka, always keep security and data governance in mind. These are crucial aspects of any data-driven system. And remember, the landscape is always evolving. Stay curious, keep learning, and keep pushing the boundaries of what's possible with Kafka.
Couldn't have said it better myself. Thanks for joining us for this deep dive into Apache Kafka. We hope you've enjoyed the journey and learned a ton along the way.
It's been a pleasure sharing our insights with you.
Until next time, keep exploring the fascinating world of data.
And keep diving deep.
That's a wrap, everyone.